Hello and welcome to the Northwest Quantum Nexus seminar series. Today we are pleased to welcome Professor Mark Saffman from the University of Wisconsin-Madison, who will talk about circuit model quantum computing with neutral atom qubit arrays. We do have a disclaimer that this seminar is being recorded. By attending this meeting, you may appear as an attendee in the recording. Your questions and comments in the Q&A will also be a part of the recording. If you have an issue, please go ahead and leave the meeting. We also have a code of conduct. The NQN is dedicated to providing a respectful, friendly, professional experience for everyone, regardless of gender, sexual orientation, physical appearance, age, race, or religion. We do not tolerate any behavior that is harassing or degrading to any individual in any form. Individuals are responsible for knowing and abiding by these standards. We encourage everyone to assist in creating a welcoming and safe environment. NQN reserves the right to refuse admittance to or remove anyone from an event at any time at its discretion. Now I will turn it over to Neri, who will be giving an introduction to Mark Saffman.
Thanks, Mark. Good afternoon. My name is Neri Govin. I'm a physicist at PNNL. Please join me in welcoming Professor Mark Saffman to the Northwest Quantum Nexus seminar series. Professor Saffman is a professor of physics at the University of Wisconsin-Madison. He is the director of the Wisconsin Quantum Institute and chief scientist for quantum information at Cold Quanta Incorporated. He is a fellow of the American Physical Society and the Optical Society of America and has been recognized with the Alfred P. Sloan Fellowship and a University of Wisconsin-Willis Associate Award. He also serves as an associate editor for Physical Review A, and most recently is a key investigator on the recently funded QNext NQI Center, which is led out of Argonne National Laboratory that PNNL is also a part of. Professor Saffman is a pioneer in the development of quantum computing with neutral atoms. Today, he will be speaking to us about his exciting work on circuit model quantum computing with neutral atom qubit arrays. Go ahead, Mark.
Thank you, Neri, and thank you for the invitation to present to the Northwest Quantum Nexus seminar series today. It's my pleasure to do so. Let me go ahead and share my screen. Let's see here if I can get the right window. And that is, are you seeing my first page?
Yep, we are good to go.
Very good. Okay, so I want to tell you about our work on circuit model quantum computing with neutral atoms. And I'll tell you about work that over the years has been done at my university group, and over the last few years has also involved a very close collaboration with Cold Quanta, who are working to commercialize this approach to quantum computing. And so I'm going to give a bit of background and tell you about recent progress and also what we're working on now on implementing NISQ-era algorithms and circuits. And time permitting, I'll tell you about some less published ideas about a new atomic approach to quantum computing. So let me turn on my laser pointer here. And so quantum computing, there's a lot of activity in this field, as I'm sure we're all aware. And there are a handful of platforms that are being very actively developed to provide quantum computing capability. And roughly speaking, you can divide those platforms into atomic approaches using either neutral atoms or trapped ions. And you can contrast those with engineered qubits, superconducting circuits, quantum dots, and then I put off to the side the optical approach. And I don't think I want to take too much time to go into details about the characteristics of these different approaches. To be honest, I will say that all platforms for quantum computing have pluses and minuses. Some things are easy for some platforms, Some things are difficult for other platforms. I don't think quantum computing in general is simple for any approach. And it's a truism to say that quantum computing is hard. And it's hard because we're trying to satisfy conflicting requirements. On the one hand, if we have a collection of qubits that we're using for our quantum computation, we have to be able to control the quantum states in a very complete manner, and we need to be able to couple those qubits together to get interactions, to perform computations. At the same time, the quantum properties rely on very weak coupling to the environment in order to preserve the non-classical aspects that lead to computational speedup, including quantum superposition, quantum entanglement. And so we need to isolate the qubits from the environment. On the other hand, we need coupling to the environment in order to read out the results of a computation and eventually to implement error-correcting protocols to make the computation scalable. So we need to have the qubits perfectly isolated from the rest of the world, yet we need to be able to go in and control them. And so those conflicting requirements make this a hard task to solve. And indeed, if you think about the history of ideas behind quantum computing, the initial ideas date back about 40 years now to the early 1980s, that this using quantum systems to perform simulation or computation was going to be potentially very valuable. Those ideas are 40 years old. The first quantum logic experiments, which were done with trapped ions, are now 25 years old. And we've been in this, say, acceleration commercialization phase with large industry involvement for the last more than 5 years now. Yet you still cannot go out today and buy a practically useful quantum computer. So undeniably, it's a big challenge. And to solve that challenge, we need to think carefully about what approaches should be used. And although an atomic approach has not been the one that's had the most attention in the last 10 to 20 years, we think there's good reasons to expect that an atomic approach is actually going to end up working extremely well. And one of the advantages that we see in using atoms for qubits is that, in a sense, we can solve this challenge of having both isolation and control in one system. So our basic platform is to laser cool atoms and then trap them using patterns of light in a vacuum cell. So here you see an image, a fluorescence image of a two-dimensional array of individual atoms. Each one of these blue spots corresponds to a single trapped atom. And these trapped atoms are exquisitely well isolated from the environment and from each other, such that quantum properties can be maintained for quite long timescales, seconds to minutes. At the same time, we can then take laser pulses, focused laser beams down to individual sites, and using pulses, excite these atoms in their ground state up to highly excited states, Rydberg states. And when we excite a pair of atoms to Rydberg states, they interact extremely strongly with an interaction strength that's 12 orders of magnitude larger than when they're trapped in their ground states. And so we can both have isolation when we're using the atoms as quantum memory, and also strong interactions that we need for logic in one system. And this ratio of 12 orders of magnitude is possibly unparalleled in any other platform. So that's one aspect of this atomic approach. Another important aspect for scaling computation is the connectivity. And I'll come back to this in more detail, but because of the strength of the Rydberg interaction and its long-range nature, we anticipate that eventually we'll be able to fully connect up to something like 60 qubits. That is to say, in a single step, any pair of qubits sitting within this outer circle could be entangled with a gate operation. And the connectivity is also reconfigurable because it depends on where we shine our laser beams. And that can be contrasted, for example, with modern state-of-the-art superconducting circuits. This, for example, is a picture of the connectivity graph of IBM's Hummingbird chip. And in these systems, the connectivity is at best nearest neighbor, but in fact, even less than nearest neighbor in this large chip structure. And the connectivity has an importance, and there's different ways you can think about it, but let me try and give you a simple way of thinking about the value of connectivity in terms of implementing quantum algorithms. Supposing I'm trying to run a quantum circuit that requires an entangling operation between a qubit sitting over here on the left and a qubit B sitting over here on the right. Well, if I'm working in a system with only nearest neighbor connectivity, then in order to entangle those two qubits, I'll have to do a series of swap operations to move A over here, and then a final entangling C0 gate. Each quantum swap takes 3 C0 gates. So to get from there to there, I need a total of 28 gates. And even if each gate had a high fidelity, to taking that number to the 28th power, I'd be down to about a 0.75 fidelity. Not so great. On the other hand, if I have a system with long-range connectivity, for example, a Rydberg gate atomic system, I might be able to go from A to this point in the middle in a single swap operation. That would be 3 gates, and then a final entangling gate, so 4 gates total. So that same 0.99 fidelity to the 4th power would still be a number that's quite high. And even if I started with a lower fidelity, I'd end up with something higher than I had over here. So it's really the combination of connectivity and intrinsic fidelity of the gate operations that is going to end up having algorithmic importance. So we think this connectivity feature of the atomic approach is also going to be important as we scale these systems up. So with those words of introduction, to give a bit more background, I guess continuing introduction about neutral atom quantum computing, here's a very brief history. The original ideas for using qubits encoded in neutral atoms date back to the late 1990s, early 2000s, really the same era when quantum gate ideas were being proposed for a number of systems. And a few years later, in the early 2000s, we had the first experimental demonstrations of quantum state control of single trapped neutral atoms. The better part of a decade later, in 2010, we had first demonstrations of a universal gate set, that is 1-qubit gates and 2-qubit entangling gates, and preparation of entangled Bell states of neutral atom qubits. And that was done by us in Wisconsin, and also a group in Paris, near Paris at the Institut d'Optique. And a few years later, we started seeing systems with arrays of tens of atomic qubits. And just a couple of years ago, we got into what I think of as the high fidelity era, where a pair of atoms was entangled with a Bell state fidelity greater than 2 nines by the Endress group at Caltech using strontium atoms. And what we're trying to do now is to combine high fidelity operations with multi-qubit arrays and really build a computer that we can use for running algorithms and doing computations. So we're about 20 years in since the initial ideas, and it's an exciting time in the field. Now, the experiments to date have taken place in rooms that look like this, with this kind of beautiful chaos that you encounter in an atomic physics lab, way too many wires and connections, but over here in the back is our quantum processing unit. And a little bit closer up, you see setups that look like this. Somewhere in the middle here, out of sight, is a small vacuum cell where we actually have the trapped atoms that we use for the operations. So the processing unit is this kind of scale, and then there's a couple tables of lasers and electronics that feed into this to actually run the experiment. And I'll just say, I'm not going to talk so much about what Cold Quant is doing, but part of the effort there is to take these larger rooms of equipment and engineer it and make it reliable and more compact, and really get to where we have a more turnkey capable computer. So for any implementation of a quantum computer, there's a set of requirements that are needed. We need to initialize qubits. They need to have good coherence. We need to be able to measure quantum states. We need a universal set of logical gates, and it has to be scalable if we're going to get to a level where we go beyond what's possible with a classical computer. And scalability in many cases is a nut that's hard to crack, and it's also somewhat unpredictable because one may think one has a scalable system, but perhaps in the end it turns out not to be scalable because of something that was not considered in the analysis or design. So the only way to really prove scalability is to build the thing and see how well it works. And we're at a stage now where a number of academic research groups around the world have built systems with more than 100 qubits now, primarily for quantum simulation so far. But I think we're also going to see that, we'll be seeing that for circuit model quantum computing in the coming year. So this atomic approach is based on atoms, and we have a whole periodic table of atoms that we might pick from. And this is my version of the periodic table, which is colored in to indicate the elements for which laser cooling and in many cases also trapping has been performed. And so there's quite a few different elements that have been used, that have been laser cooled. And in terms of arrays of single atoms that can be used for quantum information, really 4 species have been used for that. The alkali atoms, rubidium and cesium, that were initially used, and just in the last couple years, there's a rapidly growing interest in the alkaline earth, strontium, and alkaline earth-like atoms, ytterbium, that have some unique properties that make them also very attractive for quantum information. So I'm going to primarily talk to you about cesium, and I like to think of cesium as an industry standard qubit. Here's electronic, or the electron distribution of the ground state of cesium, and this is the hyperfine structure of the ground electronic state, and the m=0 clock states of the cesium atom provide the international definition of the second today. And we're going to use that international standard as our cesium atom qubit, the m=0 clock states. It's perhaps interesting to note that these states are in fact themselves entangled states. These two m=0 Zeeman substates are plus and minus parity superpositions of the electronic and the nuclear spin projections being opposite, giving total spin projection 0. And so those are in the nuclear and electronic degrees of freedom entangled states. It's not the kind of entanglement that's useful for computation, but these states are excellent states for encoding qubits in because they have very good coherence properties. Even though this state is a little bit higher in energy than the lower state by about 9.2 gigahertz, in free space, those states have very long lifetimes. It's about 34 years in free space, so that's many graduate student lifetimes, so that's a good long time. And when we optically trap these atoms in the qubit array, the trapping potential, as well as other external fields like magnetic fields, does introduce some decoherence of the qubits, but longitudinal and transverse coherence times up to about 10 seconds have been demonstrated, and the coherence is limited by atomic temperature, trap light, optical Stark shifts that differentiate between the states, and also quadratic sensitivity to magnetic fields. We believe that with coherence engineering of the traps, so-called magic trapping approaches, this 10-second or so can probably be pushed up into the minute scale. That remains to be demonstrated, but we see a path forwards towards getting extremely long coherence times. The control knobs we have for working with the atomic qubits are basically microwaves and lasers, mostly lasers. In our lab, we use something like 6 different colors and about 13 different lasers. That's why there's a whole room of equipment. There's a lot of complexity in these systems. And we use those lasers for trapping, for cooling, for state preparation by optical pumping, for measuring quantum states, and also for the gate operations that implement quantum logic. So what's the operational sequence that we go through? There's the first set of steps which are about controlling the mechanics of the atoms. And that is to say, we do laser cooling using quite standard techniques, and this uses a couple different lasers, the way we do it. We then load those laser-cooled atoms into an array of optical traps defined by light that uses another laser wavelength, and then we do some further cooling on the trapped atoms. And then we rearrange the atoms using yet another laser to fill, or at least partially fill, the array. So that's controlling the mechanics. And then there's a calculation cycle, which involves state initialization into a well-defined Zeeman substate by optical pumping. Then we execute our quantum circuit, and then we measure the results. And then this cycle can be repeated many times until eventually we'll want to start over, recool, and reload the array. So I'll first speak to some of the techniques that go into this part of the operations, that is controlling the mechanics, and then speak to the quantum computational part. So for optical trapping, we actually use 2 different types of optical traps in different parts of the experimental sequence. We use red traps, where atoms are confined at a local maximum of the optical intensity. And this is most simply done by just taking a Gaussian laser beam and focusing it to a small point. And then the atom is trapped where the intensity is high. And this is useful for moving atoms around and filling the qubit array. For the actual computational qubits and calculations, we use blue detuned optical traps. And so by changing the wavelength of the trapping light, we can use colors of light which are repulsive for the atoms. Even repulsive light can be used to trap atoms by forming a structure that has a dark spot surrounded by light in all directions. And if you can put the atom inside that, what we call an optical bottle beam, or 3-dimensional blue detuned trap, then the atom gets trapped at a position where there's very small light intensity, and that gives less perturbations to the atomic qubit, so that's used for holding the qubits while achieving long coherence times. And there's different ways of making arrays of these blue detuned traps, and in my group, this is something we've worked on for a long time, starting with our first foray into single optical bottle beams more than a decade ago. Then we made arrays of bottle beams, and then we went to something we called a Gaussian beam array with overlapping Gaussian beams, and did small arrays and then larger arrays. And now we use something called we call a line array, which is a grid of intersecting lines. And these are blue detuned repulsive lines, and the atoms get trapped in the boxes in between each unit cell of lines, and are actually trapped in 3 dimensions, because if you propagate out of the plane of this picture, those lines will spread and fill in due to diffraction of the light, giving a 2-dimensional array of 3-dimensional traps. And using that technique, we've trapped arrays up to several hundred atomic qubits. And in fact, we think we can scale this up to 500 or so. And so this is actually a picture not of the atoms, but of the light. And the arrangement of grids is controlled by a computer driving a modulator. And so we can even dynamically change the size of the array. We're currently working on some extensions of this kind of design that should be able to trap up to several thousand qubit sites. When we load atoms into an array like this from a background ensemble of laser-cooled atoms, the loading of single atoms is stochastic. So loading atoms into a trap array, we get pictures like this, where we see some of these sites have single atoms and some of the sites are empty. And then those arrays can be deterministically filled by taking a picture, seeing where the atoms are, and then moving the available atoms around to completely fill a contiguous subset of the array or to make any desired pattern. And perhaps the most striking example of that is this beautiful picture from Antoine Brouet's group from a couple of years ago, where they made a small Eiffel Tower built up atom by atom. So really quite remarkable what one can do moving atoms around. We've also started implementing this on our 2D array using a scanning module here. And here you can see just some first steps in this direction for us, where we spelled out cold quanta using atoms arranged on a 2D grid. So I hope that gives you a flavor of how one actually works with these, moving these atoms around, atom by atom. That's the controlling the mechanics. And then there's the calculation cycle where we perform quantum computations. To run quantum circuits, we need a set of gates. And our gate set is shown here. So again, we're using these m=0 clock states of cesium. And we have a couple capabilities for implementing gates. We can perform gates in parallel on all qubits using microwaves, which address the entire array at one time. That gives us global rotations. We can combine the microwaves with optical Stark shifts using lasers that are focused to single sites at a time. That gives us local rotations on single qubits. And then we can perform controlled Z gates between pairs of qubits using the Rydberg blockade. And those controlled phase gates can be converted into C0 or controlled X gates by combining the Rydberg interaction with local rotations. Also, native multi-qubit gates are possible with this atomic platform. Both gates with multiple targets and also gates with multiple controls. And for example, the Toffoli with 2 control atoms was demonstrated in a really nice experiment by Lucan's group at Harvard quite recently. So here's an example of global rotations on these atomic qubits, where we turn on resonant microwaves and we execute Rabi oscillations on all the qubits in parallel. And the fidelity can be characterized using randomized benchmarking. And it was between 2 and 3 nines in this experiment. To turn this into site-selected single qubit operations, we can detune the microwaves and add a local Stark shifting laser so that only one site becomes resonant. And so you can, for example, rotate the qubit in the single site while not perturbing the neighboring sites. And this has been done with fidelities of around 2 nines and crosstalk about the 1% level. And this experiment this was actually about 5 years ago already now. There's different ways of actually doing this. I think I'll skip these next 2 slides in the interest of time and just go on to the atomic interactions with Rydberg states, which is what enables the 2-qubit entangling operations. So when the qubits are sitting in the atomic ground states, they're very well isolated from the environment and also from each other. The interaction at a 3-micron separation, which is characteristic for our optically trapped arrays, is about 1 millihertz. So a very weak interaction when we're using the qubits as quantum memory. And then we shine laser pulses and excite up to these Rydberg states. And because this interaction is very strong, there's a Rydberg blockade phenomenon which prevents 2 close by atoms from being simultaneously excited. And as I said, this interaction strength between the Rydberg atoms is greatly larger than the interaction between the ground states. And that's true for almost any of the Rydberg states up here close to the ionization threshold. We can look at this a little bit more quantitatively on the next slide, where you see the strength of the interaction versus the atomic separation as a function of the different levels. So here's the ground state interaction. which is dominated by the magnetostatic dipole-dipole of the electronic spins. So it's a 1 over r cubed interaction, and it's sub-hertz for anything over a fraction of a micron in separation. And as we go higher and higher in principal quantum number, we get a stronger and stronger Rydberg interaction. And that's the basis for saying we can get to, we believe we'll be able to get to something like 60 fully connected qubits, given the spacings we're working with and given the range of this interaction. Our latest designs for quantum gate protocols require only 10 to 20 megahertz of interaction to have a high fidelity entanglement. And so that really translates into a large block of fully connected qubits. So putting all those pieces together, the main features of the experimental geometry is that we have an array of qubits trapped in a vacuum cell. We can apply microwaves to rotate all the qubits in parallel. And then using focused laser beams that come from two sides, we can perform localized gate operations. And that involves a blue laser and an infrared laser. The blue laser and the microwaves give us single qubit gates, and the blue plus the infrared give us the Rydberg excitation for the 2-qubit gates. So there's actually a lot of different pulse protocols that enable entanglement to be achieved. This is the original protocol from 20 years ago, which involves a 3-pulse sequence, a pi pulse on the control qubit taking up to a Rydberg state, a 2 pi on the target that rotates it, and then another pi pulse on the Rydberg state. And when both atoms start in this upper hyperfine state, the qubit 1 state, which is resonantly coupled to the Rydberg state, then first exciting the control atom prevents the excitation of the target due to this blockade phenomenon, which shifts the level. And then when we return the control qubit back to the ground state, it's executed a full rotation, which gives it a -1 phase. So in the ideal limit where we neglect Rydberg decay and neglect the finite scale of this interaction, we can get ideally a perfect controlled phase gate. And again, this is the original protocol. There's many other gate protocols that have since been developed, and some of the newer protocols are going to have much better performance than this initial idea. Here you see the basic nature of this conditional dynamics due to the Rydberg blockade. What I'm showing here is the result of essentially a Ramsey interferometry experiment, where we put this qubit in a superposition state using a microwave pulse. We do a 2 pi Rydberg pulse, and then another pi/2 rotation with a varying phase. So that gives us this red curve of the output population. And then if I do the same thing, but first excite a neighboring atom to the Rydberg state, which blocks this Rydberg excitation in the other atom, then I get again an oscillatory curve, but which is pi out of phase. And so that pi phase shift between those two curves is just that Rydberg blockade interaction. So one can then combine these steps together with local pi/2 rotations and implement a C0 gate. And this is our so far best result to date in this kind of dense array, where we got to about 89% Bell state fidelity. And this is really not a fundamental limitation, but entirely technical, limited by laser noise, optical stability, and also finite atom temperature, and that the atoms moving around, giving Doppler shifts, but also moving to different positions under the addressing laser beams leads to errors in the gate implementation. In a reduced geometry, much higher fidelity has been demonstrated, and one of our goals is to achieve that higher fidelity in this kind of dense array. In fact, if one looks at different platforms and how they've evolved over time, really for all the approaches, there's been an increase in fidelity between the initial demonstrations and when high fidelity was achieved. trapped ions achieved the first entangling gates in 1995, and a decade plus later, they got to this very high fidelity level. And the same has been true for superconductors and quantum dots. Gold atoms had their first entangling gate demonstration later than these other platforms. And we're just now, in the last year or so, getting into this high fidelity regime. We're confident, based on our understanding of the physical system, that we're going to be able to get there, but still not yet being shown in these dense two-dimensional arrays. If you think about it from the perspective of physics, this is a very simple system. We know the Hamiltonian very well. It's a couple isolated atoms interacting with laser beams. We can write down the governing Hamiltonian from first principles. We can solve it. We can numerically analyze it. And we're quite confident we're including all the important contributions to that Hamiltonian. So if we can implement the correct engineering to implement that Hamiltonian effectively, we're confident we will arrive at very high fidelity gates in large arrays. So lately, a lot of what we've been doing is engineering systems. This is work that's being done in collaboration with Cold Quanta, and we've in the last year and a half put in a next generation machine with a better engineered optomechanics, better vacuum cells, and a lot of upgrades to lasers and control electronics, and also testing improved gate protocols. I'm not going to have time here, but I'll just point to a couple papers where we've analyzed some newer gate protocols that I think much more directly will provide higher fidelity entanglement, and these are things we're testing out now. So that's kind of where we are in terms of building the hardware and qubits. Let me take a little break with a picture of Arizona, and maybe, I guess I'm trying to say it's a prickly path forward, but still a beautiful path forward to really turn these ideas into something that we can do science with and maybe solve real world problems with eventually. And so let me take the next minutes and talk about what we're doing in terms of starting to implement algorithms on this atomic system. So we're looking at NISQ era algorithms. One of the well-known algorithms is VQE, Variational Quantum Eigensolver, where one uses a quantum coprocessor to tackle the exponentially hard task of preparing a high-dimensional quantum state, measuring the energy of a cost function in that state, and then using a classical optimizer to vary parameters in the circuit to reduce the measured energy of the cost function, and thereby converge towards a variational optimal solution to a given computational problem. And so one problem we've been looking at within this VQE framework, and this is a DOE-funded project together with colleagues Wisconsin and elsewhere, is to use our nascent quantum computer as a testbed for studying dark matter detectors. And we don't know what dark matter is. We don't know, and therefore we don't know what the interaction Hamiltonian is between dark matter and detectors. But there are possible models for what that interaction could be. And as a first step, we're testing our digital quantum simulator using a model that we do know the solution of, the Lipkin model, which is exactly solvable, and just starting with some small scale circuits to use VQE to find the ground state of the Lipkin-Meshkov-Glick Hamiltonian, which is shown here. And here we just have numerical results so far, and there's a preprint here of numerical studies of this problem, including a noise model for our quantum system. And this shows the circuit for preparing the 3-qubit ground state of the LMG model. And when we simulate that circuit, including noise in the gates, what one sees is that although the measured energy depends on the fidelity of the gate operations, the accuracy with which the circuit can predict the correct variational parameter to find the ground state is relatively insensitive to the noise. So the amplitude changes with the noise level, but the value of the variational parameter does not. And so that's a good indicator for the potential usability of this VQE approach. So that's one activity we're engaged in. Another is the QAOA, and this is part of a DARPA-funded project tackling combinatorial optimization problems. So here we've been looking at the very well-known max cut problem, which is a graph optimization problem, which has the goal of taking a graph of nodes connected by vertices and finding a partition of those nodes into two sets such that there is a maximum number of vertices that cross the dividing line between the two partitions of the graph. And from that perspective, it's a very abstract problem, but it turns out it has a lot of applications to real world problems in resource allocation and optimization. And so as a warm-up problem, we have an example here of a 6-qubit, 3 regular graph. That is, each qubit is connected to 3 other nodes of the graph. And in an implementation of the atoms, some of these couplings are nearest neighbor, and some of the couplings are next nearest neighbor. And depending which Rydberg states we use, we'll either do those directly or with swap gates. Even though this is a relatively small toy problem, it turns out one already needs a quite substantial quantum circuit depth to implement it. And so we definitely need to improve our gate fidelity to tackle this in a useful way. One interesting aspect is that QAOA has a certain amount of built-in robustness, and that if one just considers C0 gates with an intrinsic fidelity due to imperfections, and one calculates the accumulated infidelity from the sequence of those C0 gates, that the error actually for the QAOA circuit grows more slowly due to some, in a sense, inbuilt echoing of the errors that's built into the QAOA implementation of max-cut. So this comes from numerical simulations. We'll see how that plays out in practice. Here's just the p=1 first level encoding of QAOA on that 6-node circuit, and you can see if we include swap operations, it's already quite a deep circuit. And so we've been analyzing this using a noise model, and here's some simulations actually on a 9-node graph. This is a weighted max cut where the connections have certain weights between them. And it turns out the optimal solution to this 9-node weighted graph has a cost function of -8.8. And here's the circuit needed to implement that 9-node graph if we assume that we're limited to nearest neighbor interactions. There's a total of 5 swap and 18 ZZ gates. Is actually 51 controlled Z gates per cycle. So even a relatively small problem is a lot of gates. And we've done a full noise simulation of that circuit using a noise model specified here, using really quite realistic parameters for our coherence times in the current system, the times for single qubit microwave gates, times for 2-qubit controlled Z Rydberg gates, single qubit gate errors, and then we calculated the output results varying the fidelity of the 2-qubit gates and comparing that with the noise-free performance of the QAOA circuit. And so to get close to the noise-free performance, we indeed need to push the gate fidelity up into 2 nines and above to get close either to the probability of reaching the ground state or reducing the cost function to what's possible for p=1 QAOA. So this is just preparing us for actually running the circuit on our hardware, which we expect to be doing later this year. So that's where we are so far in terms of running digital simulation circuits. And I was asked to stop at 3:45. If people don't mind, I'm going to take just 5 more minutes and tell you about one more topic, and then that'll leave another 10 minutes or so for questions. So I want to just come back to this question of what's the right atom to be using. And I told you about work with cesium. Many groups are using rubidium. It's essentially equivalent to cesium for this application. There's also groups using alkaline earth atoms. But in the atomic physics community, there's been a lot of progress with lanthanides. And so I want to tell you about an effort we've had with the lanthanide holmium. And what might a better atom give us for this application? Well, we needed an atom with 2 levels for encoding a qubit. If we look ahead towards implementing error correction, in general, for error correction, we need to be able to measure the state of an ancilla qubit without disturbing surrounding data qubits in order to implement an error correcting protocol. And we measure these atoms by scattering photons and then collecting the photons with a lens and a detector. But in fact, all the atoms in this array are resonant absorbers. So just the light scattering that we use for state measurement will disturb neighboring atoms in the array. And that's a problem if I just have 2 levels available. What we really would like is a spectrally isolated additional level that we could use for cooling, initialization, and measurement without disturbing the quantum states encoded in a qubit. And so if we had another level that was coupled to some other excited states that were well separated spectrally from the same transition out of the qubit levels, we could suppress the crosstalk due to photon scattering and therefore implement these dissipative operations without disturbing encoded qubits. So not only would that let us make crosstalk-free measurements, but we could envision doing cooling and initialization on some atoms without disturbing other qubit atoms. And so that doesn't really work for alkali atoms, where we just have these 2 hyperfine levels. You could think about doing this with optical clock atoms, and we've looked at this. It seems extremely challenging due to leakage out of excited state manifolds. If we thought about doing the measurement within the metastable excited states. And the lanthanides, which have a more complex structure, seem to be one way of doing this. And so, for example, holmium has the most complex ground state of any stable element. This is the ground hyperfine Zeeman structure of holmium, has 128 magnetic hyperfine states and large hyperfine separations between these 8 levels. So ranging from 8 down to about 4 gigahertz. Holmium, despite its complexity, has some remarkable coherence properties. Here's an experiment done in Germany some years ago where they implanted holmium on top of a surface, and due to the symmetry of the surface and the holmium atom, they were able to observe spin coherence times of many minutes in this configuration. That's not to say you could directly use that for quantum computing, but it is something interesting to think about if we could find some way of preserving the coherence of holmium and also using it for quantum computing. In my group, we've done gas phase cooling and spectroscopy of holmium. We did laser cooling and made a magneto-optical trap. We've done Rydberg spectroscopy on holmium and observed well-behaved Rydberg levels that could be used for gate implementation. And we've done optical trapping of holmium in a single beam red detuned trap. It does turn out that there's very strong tensor polarizability effects when optically trapping holmium, such that optical trapping does not seem ideal for achieving long coherence times. And therefore, we've considered magnetic trapping of holmium. And holmium has a large number, all the red states, a large number of magnetically trappable states. And in fact, there are many pairs of those states that can be made magic, that is, have an energy separation that's independent of magnetic field. And there's a pair of states that are low field magic. So at a small field of 3.5 Gauss, these two states have a energy separation that's independent of magnetic field to first order, and therefore provides a potentially long coherence time implementation of a qubit. And so the idea then is to use those two states for our qubit, and then use a different hyperfine level for this dissipative control to suppress crosstalk from light scattering. And then we have a conceptual design for a magnetic trap array to build up an array of holmium qubits. So this is still on the drawing board, but I see it as potentially yet another way of scaling up these atomic systems. There's also the possibility for QDIT encoding in this holmium system, which might provide a route to more efficient error correction. So I'm sorry I went a little bit over, but I'll end with a final slide. I hope I've convinced you that atomic physics supports this approach to quantum computation as having a high figure of merit, and certainly the scalability appears promising using these optically or eventually magnetically trapped arrays, and we're hoping soon to have some real results on implementation of hybrid algorithms using digital circuits. So let me stop there. Thank you for your attention, and happy to take some questions.
Thanks, Mark, for the excellent talk. So while people are typing in their questions into the Q&A window, I had a couple of questions for you. So what is, in this middle thing, you've got the scalable 2D array. What is the dimension of this thing?
Yeah, so these sites are separated by 3 microns. So this is an 11 by 11 array, 121 qubits. It's 30 microns on a side.
And how often how long do the atoms actually stay in place?
So that depends on the vacuum. We're limited by collisions with untrapped background molecules. And even in small vacuum cells, we have lifetimes of about 30 seconds. And we think we can push that up to a couple of minutes.
I see. Yeah, I still haven't seen anybody type in any questions. I'm not sure if they're having some issues with the Q&A texting. So let me ask another question. So what kinds of problems do you think, like it appears to me that there are certain problems that naturally map themselves onto an array like this. Can you comment on that? Or does it is it more amenable to certain classes of problems?
Well, what we're trying to develop here is a universal quantum computer. So we have a complete gate set. We have a eventually large number of qubits, and we have a good connectivity. So, I don't think there's one type of problem that would be more amenable. That said, if you think about the space of gate fidelity and number of qubits, and we need both high gate fidelity and large number of qubits to demonstrate a quantum advantage, it's clear that the challenge that we can tackle most directly is the number of qubits. It's relatively easy for us to get to a large number of qubits, whereas we've not yet demonstrated high fidelity in these arrays. So algorithms that take advantage of the number of qubits but have circuits of smaller depth would seem to be an interesting place to look for these types of systems, at least initially.
Thanks, Mark. I still haven't seen anybody add any questions to the Q&A.
Okay.
There does seem to be something going wrong with the Q&A. We're having Teams technical difficulties. So
it appears that way. Yeah, Nathan. Yeah. So let's ask. Oh, go ahead.
I see a bunch of questions coming in right now.
Awesome.
Maybe there was a delay. Let me see if I can just ask. So does each lattice site have one atom or more than one? Will the number of atoms in each site affect the efficiency of gates?
Yes, so each site has one atom. When we initially load the array, we do get more than one atom in some sites, but we have methods for detecting that and clearing out those multiple occupancies. So we actually have an array where we definitely have just a single atom. It's possible to design gate protocols that work on qubits encoded in more than one atom, so an ensemble qubit approach. And those are variations on the gate protocols that work for single atoms. But here we're just working with gates that work on qubits that are one atom at a time.
Great. Got a couple more for you, Mark. A magnetic array is interesting, but is it fundamentally large compared to the nice tight spacings that 2D and 3D arrays of atoms have so far achieved? How large is a cell in your magnetic array?
Good question. So I don't have the slide here. I could show you more detail of the design. In order to get, so holmium atoms are very magnetic, about 10 times more magnetic than an alkali atom because they have open F shells. And so that reduces the requirement on the strength of the magnetic field for trapping. Nonetheless, this approach would require superconducting wires to generate enough magnetic field without heating up the chip too much. And we do have a conceptual design that we think is, at the edge of what could be fabricated, where the spacing between sites is about 7-8 microns. So a couple times larger than in the optical arrays, but still relatively small and still well within the distance where we can perform Rydberg gate operations.
Hi, Mark. There's a question from the audience, an audience member that couldn't access the Q&A, which is if you could further elaborate on the pros and cons of using an array of ensembles, because we've seen some of that work, versus an array of single atoms.
Sure. So in the ensemble qubit approach, each qubit is encoded in many atoms at one time. And because vacuum mediated loss is an issue with this atomic approach, if you use an ensemble encoding, even though you lose one atom out of your ensemble, you still have most of your quantum state remaining. And so you can in principle correct for that. And so if you had each qubit encoded in an ensemble of 100 atoms, if you lost one, you'd still have, in a sense, 99% of your quantum state left, and so that's correctable. That's one advantage. The other advantage is that you have stronger coupling to light because you have more atoms, and so that's useful for fast gates and also useful for speeding up the measurements, reducing the measurement time, because you can use that ensemble to scatter more photons in a given time. So there's some advantages, and then I think the disadvantage is that because it's an ensemble, you have more complexity, you may have collisions between the atoms, and so generally it will be hard to achieve the same coherence time with an ensemble as you can with a single atom.
Okay, thank you.
I don't see any other questions in the Q&A window. So thanks, Mark, for this excellent presentation, and thank you for being available for this. We appreciate it.
My pleasure. Thank you. Thanks, everyone. Bye.
Thank you. Bye-bye.
Bye. Thanks.